In this section, we're going to look at alternating series. For the previous two tests, the integral test and the comparison test, before we applied these tests, we had to ensure that the series had positive terms. So for an alternating series, the sign of the terms alternates between plus and minus, and the ones we're going to look at are going to look like the sum from 1 to infinity of minus 1 to the n times bn, where bn is positive, or minus 1 to the n plus 1 times bn, where bn is positive. Here's two examples. The sum of minus 1 to the n times 1 over n. The 1 over n part is positive, and the minus 1 to the n part alternates between plus and minus 1. And the first term here is negative because minus 1 to the 1 is 1. It's negative 1 plus 1 half minus 1/3 plus 1/4, etc., etc. So that one's known as the alternating harmonic series. The next series on our list, the second one, is the sum of minus 1 to the n plus 1 times n over 2n plus 1. And of course, the bn, or the positive part, is n over 2n plus 1. And for this series, the first term is positive because minus 1 to the 1 plus 1 is plus 1. And then, of course, the series alternate between plus and minus. Now, in fact, that second series, we can already tell that that diverges using our divergence test. And remember, the divergence test said that if the limit as n goes to infinity of the terms of the series is not 0, then the series diverges. And in this case, the limit as n goes to infinity of the terms of the series is the limit of an alternating sequence. And we know that that limit doesn't even exist if the limit of the positive part is anything other than 0. And here, of course, the limit of the positive part is the limit as n goes to infinity of n over 2n plus 1, which is 1/2. So it's certainly not 0. And because the terms of this sequence alternate between numbers close to plus and minus 1/2, there is no limit. And therefore, of course, our corresponding series above, the second series on our list, diverges according to the divergence test. The big test in this section is the alternating series test. And it says, if I have one of these alternating series, the sum of minus 1 to the n minus 1 times bn, first thing I should check is that the limit as n goes to infinity of bn is 0. If not, then we saw, as in the last example, this series is going to diverge. And then, if bn plus 1 is always less than or equal to bn for all n, then I can conclude that the series converges. And graphically you can see the reason for this. I've drawn sort of a picture of the partial sums here. The first partial sum is just b1. And the second partial sum is b1 minus b2. But b2 is smaller than b1. So I've gotten closer to the center of this interval between 0 and b1. And the third partial sum, I add something smaller than b2 to it. So the result, the third partial sum, is less than b1 and greater than the second partial sum. And then I consecutively add or subtract terms that are smaller in absolute value, and you can see that the partial sums have to cluster somewhere here in this interval between 0 and b1. And because, of course, we have infinitely many of them, there must be a point here which is a limit point or a cluster point, and you can show that that is a unique limit here. So there's a full proof that there's a unique limit here to these partial sums at the end of your notes. Let's just say a few things about this test before we apply it. Theoretically, as I stated it, it applies to the sum from 1 to infinity of minus 1 to the n minus 1 bn, But of course, if I replace that minus 1 to the n minus 1 by a minus 1 to the n, the same conclusions could be reached. If conditions 1 and 2 are met here, this series converges. And also, we don't really need bn plus 1 less than or equal to bn for all n, as long as that happens for n bigger than some number, 100, 1 million, or from some point on, then we can conclude that the series converges. And of course, this is because what happens to the first few terms of the series doesn't really affect convergence or divergence. Recall also, if we have a differentiable function, f of x, when we replace the n by an x in the formula for the positive part bn, then we can use the derivative to check if these terms are decreasing. Well, let's test the following series, the alternating harmonic series for convergence. First of all, the limit as n goes to infinity of the positive parts of these terms, the limit as n goes to infinity of 1 over n is 0. Certainly, convergence is a possibility here. The divergence test doesn't allow us to rule out convergence. And the second thing we have to check is this condition that bn plus 1 is less than or equal to bn for all n. Now here, bn plus 1 is 1 over n plus 1, which is indeed less than 1 over n for all n bigger than or equal to 1. So both of these conditions for the alternating series test are met, so we can conclude that the alternating harmonic series converges, in contrast to the harmonic series itself, which we know diverges.